Welcome back. In this video, we're going to look at ellipses, and we're going to look at the geometric definition of an ellipse first. An ellipse is the set of all points in the plane that the sum of their distances from 2 points, called the foci, is constant. If I were to take 2 points inside an ellipse, and I were to get a little piece of string and dangle it, so it's kind of just hanging loose on these 2 points, and then I were to snag that with, say, the point of a pencil, and I were to just run this snug line along, it would create an ellipse shape. And I would encourage you to even try it yourself. So let's look now at the equations of an ellipse. First, we're going to look at an ellipse with center at the origin. The graph of each of the following equations is an ellipse with center at the origin and has the given properties. The equation has an x squared over a squared plus a y squared over b squared, and it's equal to 1. If we let a be greater than b, which is greater than 0. So if I were to highlight the larger denominator, it would be the first one, or the one under the x, for a more horizontally smushed type of ellipse. Now, if we're looking at the second example here, we have x squared over b squared plus y squared over a squared. Notice that a is the larger value, which is larger than b, which is larger than 0. So if I compare these, now my larger denominator is paired with the y's, the y direction instead of the x direction. So the vertical direction is now this smushed vertically ellipse. It's taller in the y direction than it is in the x direction. And with this other one, since a is larger and it's in the denominator of the x squared, the ellipse is wider than it is tall. The vertices of this ellipse will be plus or minus a comma 0. Now, if a is the wider direction, so we can think of vertices as kind of like a vertex of a parabola, but in this case it's a closed shape, and so our vertices are plural now, and we have these vertices existing on the farthest or widest edges of this ellipse. The major axis for the wider, not taller, ellipse is the horizontal length 2a, the horizontal axis. The minor axis in this particular case is the vertical axis. So the y-axis is now my minor axis because the ellipse is shorter on that side. And if we wanted to talk about the foci, we can see that the foci are going to be at plus or minus c comma 0, where c can be found by using this formula. C squared is equal to a squared minus b squared. And similarly, you can do the same thing with the ellipse where the foci are at 0 plus or minus c. This is where the ellipse is taller than it is wide. And the vertices are at 0 plus or minus a. Now, a lot of this stuff I'm just trying to show you patterns so that when you're trying to do this on your own, hopefully you're remembering some of this stuff. This is a lot of information all at once, but I think that you I think that you need to figure out ways to process that information. So finding patterns that exist is one of the ways to do that. In the standard equation for an ellipse, a squared is the larger denominator and b squared is the smaller. This is what I was just showing you with the equations. To find c squared, subtract the smaller denominator from the larger one, which makes sense because you don't want a negative c that you have to take the square root of. That would not make any sense. So let's look at the definition of eccentricity. For the ellipse, x squared over a squared plus y squared over b squared equals 1, or similarly, x squared over b squared plus y squared over a squared equals 1. The eccentricity, we'll call it E, is the number c over a, where you can find c. Now remember, c is the value that we can use to find the foci. The eccentricity of every ellipse satisfies 0 is less than e is less than 1. And we'll be using this formula to find the value of c, but we also have to know whether it will be on the vertical axis or the horizontal axis. Let's take a look at this example 5. It says find the vertices, foci, and eccentricity of 5x squared plus 6y squared equals 30. Determine the length of the minor and major axes and sketch the graph. You can check your graph using a graphing calculator. I'm not going to emphasize that too much in this case, but I am going to show you how you can graph it. First, we're going to look at the equation given and recognize that the 30 can't be 30. It has to be 1. So the first thing we'll do is divide everything by 30, which will give me 5x squared over 30 plus 6y squared divided by 30 equals 1. And now I'm going to reduce those fractions. 5 and 30 reduce, and I'm left with a 6. 6 and 30 reduce, and I'm left with a 5 in the denominator. That gives me x squared over 6 plus y squared over 5 equals 1. Looking at my denominators, I know that the larger of the two denominators has to be a squared. So a squared equals 6. That means b squared equals 5. So a is going to equal plus or minus the square root of 6, and b is going to equal plus or minus the square root of 5. To find c, we use the formula c squared equals a squared minus b squared. Therefore, c squared equals 6 minus 5. And so c is equal to plus or minus 1. If I want to find the eccentricity, I calculate that E is not Euler's constant. E is eccentricity. And it's c over a, where we get 1 over root 6. Now, this is telling us how much smushage there is on the ellipse, how much it's been squished either vertically where the major axis is the y-axis, or if it's been compressed horizontally and the major axis is the x-axis instead of the y-axis. This is not a huge number. We can find out exactly what it is. So it's 0.41, which means that it's going to have a fairly circular shape to it. The closer to 1 it gets, the more extreme your ellipses start looking. They'll look more like baguettes than they do nice loaves of bread that are kind of shaped like this. So the the foci are closer to the edges of the ellipse instead of closer to the center with more space toward the outside. Recall that if we want the horizontal length, that's going to be 2a, which is equal to 2 times root 6. And if we want the vertical length, we use 2 times b, which is equal to 2 times the square root of 5. And then again, we can use the formula c squared equals a squared minus b squared to find the value for c. We now have pretty much all the information we need to graph this thing. Since the larger number is under the x squared fraction, or in the denominator of the x squared fraction, we know that the major axis will be the horizontal or x-axis. This also will tell me where my vertices are. Remember, my vertices are found for values of a. So I've now marked this out. So 2 notches on the graph represent 1 unit of shifting or moving, counting, whatever you want to say. So now we're going to label these. My c values will be at plus or minus 1. My a values are going to be at plus or minus the square root of 6. And I know that plus or minus the square root of 6 is going to be 2.4, plus or minus 2.4. So I'm going to find approximately those points and label them. So those are the edges of my ellipse. Now I need to figure out how tall this thing is. So I've gone ahead and found what the value for 2 root 6 is going to be, and also 2 root 5. 2 root 6 is 2.89897. So I'm going to round this to 1 decimal place because my graphing is not going to be that precise. So I'll be at 4.9. I'll be at 4.9 and at 4.5. My horizontal length is going to be half from the origin, half of 4.9, which is 2.45. So I will go ahead and mark those points, which is what I already have here. Now my vertical length is 4.5, which means half of that is 2.25. And so I'll count up 2.25 and down 2.25. And so now I have enough information to draw this ellipse. And then connecting my dots. As you can see here, there's not a ton of difference between this and, say, a nice round circle, but it is a little wider than it is tall. Now, if we want to find the equation of the ellipse with foci on the y-axis that has a major axis of length 4 and minor axis of length 2, we have all the information we need here to create the equation. Let's draw what's going on. We know that it has a major axis vertically, so it's going to be a more vertically tall and not very wide ellipse. We also know that the foci are going to be on the y-axis, along the y-axis, and not along the x-axis. If the major axis is length 4, then we know that 4 is equal to 2 times a, because the larger denominator is considered to be a. So that means a is equal to 2. That means I can count 1, 2. That will be the point for the edge of my ellipse. Here's my other point. The minor axis has length 2, which means its width is going from -1 to 1. So that was pretty easy to draw. And now we just need to figure out what the foci are going to be, because I can now sketch this ellipse fairly confidently. I just don't know where the foci are. But I will say that I know that the minor axis has length 2. That means 2 is equal to 2b, and that means that b is equal to 1. And now that I know a and b, I can write the equation. I know that my minor axis is the x-axis, which means that my smaller value will be under the x squared. So I'll have x squared over 1 plus y squared over 4 equals 1. And there's the equation. I don't really need to find the eccentricity. I don't even really need to find c, but we'll go ahead and find it anyway. C squared is equal to a squared minus b squared. That means c squared is equal to 4 minus 1. So c squared is equal to 3. And so if I take the square root of both sides, I get c is equal to plus or minus the square root of 3. And if I wanted to figure out what that actually was as an approximation, I just take second square root of 3, and I get 1.7 approximately. So plus or minus 1.7. There are my foci, really close to the edges here in this case. So I think that's important to note when you're making these ellipses, how the eccentricity works. This one has a much more extreme shape than the previous ones did. The closer to a circle you get with these ellipses, the closer to 0 your eccentricity gets.